All right. So let me just go to full screen. Okay. So basically, the idea is to go through the Laplace transform so that we have algebraic representation of differential equations. And the thing that will happen here is that instead of having differential equations that are functions of time, we will have algebraic equations that are functions of complex variables. And once you're done with the analysis, you do the inverse Laplace and you can obtain the solution to the ODE, which will essentially tell you the behavior of the system as time varies. So most of the control design in this course will happen in the complex domain after the Laplace transform. For those of you who are CIC students, this is also what you're going to see in 316, CIC 16, which is the course after this one. You will do design in the complex domain. However, for advanced control tools, these Laplace transform ideas are still limited in the sense that they're only applicable to linear time invariant systems. And sometimes you have nonlinear dynamics, things that are a little bit more complex. So these methods will no longer work. However, they're enough for this, but they are not that generalizable to general differential equations. So if you have a highly nonlinear system, or if you have a system that is time varying, then what happens by time varying, I mean the relationship between the input and the output changes with time. So not only the functions are functions of time, also the relationship. Imagine that if you have a changing mass, or if you have a changing coefficient of friction, things like that, then we need to use other techniques. So this is, in a sense, in classical control, we work in the complex domain. And we also defined it. So this is just to give you an idea. So basically, you would have a differential equation after the modeling. Then you use the Laplace transform to have an algebraic equation. And you can see here how simple it is. And then you go back through the inverse Laplace transform. So again, f of t is real variable, t is a real variable, it's time, and f is a real function. But after the Laplace transform, we work in the complex domain, or the frequency domain, in which the function f has another representation, capital F is the Laplace transform of small f, and it's a complex valued function. We define the Laplace transform to be the following integral. So you have a function f. You want to find the Laplace transform of it, which is capital F of S. We use capital letters to denote functions in the frequency domain. You just multiply that by the exponential here, e to the power of minus st, and you take the integral with respect to t. So once you take the integral with respect to t, you will have a function of s. Why? Because if you integrate a function of two variables with respect to one of them, then the result is a function of the same variable. Then we discussed some examples for the unit step, for the shifted step. And we had a refresher on integration by parts, and we talked about the ramp function and the exponential. We talked about the existence of Laplace transform. So a Laplace transform may not converge because this integral is improper. So there are conditions that guarantees that the transform will exist. For example, if f of t is piecewise continuous and it's of exponential order, meaning that if you take the absolute value of f of t for all values of t greater than capital T, and you can find some m, some alpha, and a capital T such that this inequality holds, then you're done. For example, if t is the sine function, then you know that it's always less than 1. So I can set alpha to 0 and m to 2 or 5 or whatever number greater than 1. And we know that for sure that the magnitude of the function is less than that value. So it is called of exponential order. Then we had a few examples in which we found values for m, alpha, and t. For example, this function For all t greater than capital T, or let's say T naught, T naught here is 0, the function will never exceed 1. So if I take m to be any number greater than 1 and alpha take it to 0, then we're done. Similarly for the sine function. Here we have 2 to the power of x. Notice that is 2.7 something, right? So we can take that and assume alpha to be 1, so that basically what happens is that 2 to the power of t, this is t, is less than, take m to be 1, to the power of t. With that, m is equal to 1, alpha is equal to 1, and t naught is equal to 0. And that inequality is satisfied. So here the function is of exponential order, and hence we can find the Laplace transform. As a recap, the Laplace transform is very useful in solving linear differential equations. And once you do that, then you can use it to analyze and design control systems. This is the definition of the Laplace transform. Capital F of S. S here is the complex variable that replaces t. We use L braces of t, and use this integral. And we have sufficient conditions for the existence of L, meaning these conditions are f being piecewise continuous and it's of exponential order. Now, if I don't satisfy these conditions, it does not mean that Laplace transform does not exist. It only means that we are not sure. But if you can ensure these conditions, then for sure that you will have a Laplace transform. Any questions so far?
Clear, doctor.
Okay. The reason I stop here is because if we move fast and there are no questions, it's okay if everything is clear, but if there is something that's not clear, it means we will move fast and then we will have homework, quizzes, tests, things like that, and things that might not be clear. So if there's something that's not clear, please let me know. All right. So we have here some useful identities from mathematics that we will use, and they will prove to be useful. So e to the power of j theta is simply cosine theta plus j sine theta. This is Euler's identity. Theta here is in radians, by the way. Now, similarly, e to the power of minus j theta is just cosine theta minus j sine theta. With some tricks, you can show that cosine is 1 over 2 of e to the power of j theta plus e to the power of minus j theta. Can we prove this? It's easy to show it, right? If I add the first two here, then these two will cancel out. Then we'll have 2 cosine is equal to this guy plus this guy, right? Divide by 2, and you're done. You get this equality. Similarly, you can find this other equality, which states that sine of theta is equal to 1 over 2j e to the power of j theta minus e to the power of minus j theta. Basically, you subtract the other one from the first one. With these useful identities, I want you to grab a piece of paper and try to find the Laplace transform of sine omega t. So let me just write down for you the equalities that you need. Let me see how to put this. I'll do a small modification here to the slides. Okay, so this is the Laplace transform. This is the definition, and we have these identities. Use them to find the Laplace transform of sine omega t. Notice the following, that this is the final answer for sine omega t, right? So it's given to you, so you can verify your answer. Take 5 minutes, let's say, and find the answer to that question. Can you guys do it?
We'll try.
We'll try.
Yes, give it a good try, because the reason I ask you to solve these things, because I do expect you to be able to do it. In tests and homework and pretty much everything, you will be asked to Laplace transform all the time in this course, an inverse Laplace transform. You should be able to do it comfortably. So this is good practice. So I'll set a timer for 5 minutes, and please start now.
دكتور، هل نحتاج integration by parts؟
I don't think so, no. But if you can do it by parts, do it. Time is up. Any luck, guys? Do you need more time? Or you gave up? Or you have success? What's going on? Tell me.
Can you solve it?
Okay. Anyone was able to do it? Okay. Have anybody, let's say, got stuck somewhere halfway? Yes, Mazen.
Yes, I wrote the whole integration, but at the last part, I don't know how to complete it.
Okay, let's do it together. All right. So we can use this identity, and we will use this definition, right? So here is what happens. Let me use another color. I always use red, so let me. I'll choose green this time. Okay. So if I apply this integral, well, let me just write the function. You have 0 to infinity. What is f t? It is sine, right? It's a sine function, so it's sine omega t. Then we have e to the power of minus st dt, right? Okay. Actually, green looks bad, so let me choose black. Okay. So we can use this identity for the sine function, right? So if I apply it, I'll have a constant here. I can take it outside the integral, 1 over 2j, just to get it out of the way. We have integral from 0 to infinity of e to the power of j theta. Theta here is omega t. So we have e to the power j omega t minus e to the power minus j omega t. The entire thing multiplied by e to the power of minus s t dt. Notice that I am trying to integrate with respect to t. So it is in my interest to take common factors of the to take a common factor so that I have all constants whatever like just next to t. So let me elaborate more. So again we have 1 over j before the integral. Then I can just multiply this here and multiply the same thing here. And we have subtraction, so it's like two integrals. It is two integrals to deal with. What about the constant omega? Yes, the constant. So j omega is a constant. Okay, j omega is a constant because here I'm integrating with respect to t. Actually, inside the integral, even s, while it's a variable, it is actually with respect to this integral, it's a constant. Okay. All right. So we have two integrals here. Right? We have 0 to infinity e to the power j omega, sorry, the entire thing is multiplied by t minus another integral 0 to infinity e to the power, we have minus j omega plus s entire thing is multiplied by t. Again, we have dt, we also have dt here, right? Let me erase some of the stuff here just to give me some space. Okay. Now we can integrate that easily, right? So this is equal to what? Again, I have 1 over 2j this integral with respect to t is just I divide by j omega minus s. And we have the same exponential j omega minus s t, and this is evaluated from 0 to infinity minus, similarly here. I will divide by minus j omega plus s, so I will put that use that negative sign to make this positive. And we have j omega plus s over what? Minus j omega plus s t. This will be from 0 to infinity. Any questions until here? Okay. All right. Something I did not tell you is S is simply some sigma plus j omega. With that knowledge, if I have minus s, then whatever I have here is going to be a negative number. So if I use infinity, if I substitute infinity, it will be e to the power of minus some number, t, minus infinity. This is 0 at infinity. Okay? So now if I do the substitution, at infinity, both terms will vanish, so I'll have the 0. So we have the following. Let me use yellow. Let me use this space. This is equal to 1 over 2j. The first term at infinity will vanish, so we'll have the 0. So we'll have minus 1 over j omega minus s. Similarly, for the other one, we will have minus 1 over j omega plus s. Take a common denominator. Let me just have negative sign here. Then take a common denominator. Let me erase this a little bit. If we take a common denominator, what happens is the following. We will have minus 1 over 2j if I multiply these guys, what happens? We'll have s squared plus omega squared. Why? You know what, I'm not going to skip steps here. Let me just show it. So we can use the multiplication rule. of conjugates, right? And what was two conjugates being multiplied equal to? No, these are not conjugates actually. So we have two complex numbers, and these two complex numbers are being multiplied. Then what is the result? Do you remember the formula? Yes, Abdullah.
-1.
Minus 1 what?
J times J.
Okay, so you're okay, J times J minus 1 omega square, right? So you want to multiply these two. Are you doing the multiplication? Let me go back, show you something. We had some here. So basically, if I multiply two complex numbers, then we have x1, 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 x2 minus y1, y2. So in our case, where is okay, you know what? Let's just multiply. So we have minus omega square plus sj omega. Then we have minus sj omega minus s squared, right? Here for this guy, we will have j omega plus s. For this guy, we will have j omega minus s, right? Notice the following. This term will cancel with this term. This term will cancel with this term, correct? Now, if I just write down the result, we get this guy. Let me show you. Now, this is equal to what? Minus 1 over 2j. Then we have 2j omega. I'm adding two together. Over minus omega squared minus s squared. This minus sign cancel with this one. 2j here will cancel with the 2j here. And this is exactly equal to this. Do you guys see that?
Yes, it's clear now.
Good. All right. Now, can you repeat how did we get it from the exponential? Okay, let me post the results here. So just 1 second. I will just. Okay. So this is the derivation again. Basically, basically, we have a sign function using the identity. It is e to the power j omega t minus e to the power minus j omega t multiplied by e to the power minus st, right? We can split this into two integrals. So we have this integral and we have this integral. Now, if we do an integration of this guy, it will be what? It will be 1 over j omega minus s multiplied by exponent, and then you evaluate it at infinity and at 0, and you get this guy. Similarly for here, you get this guy. Now, if you take a common denominator and do the math, you will end up with this equality. You will get omega over s squared plus omega squared. Is it clear? Any questions? Yes, Mohammed.
دكتور امين، انت تقول شو اعطيتنا علاقه حقت اس اللي هي يساوي سيجما بلس شيء وبعدين على طول صارت 1.
Yes, okay, so that was just to say that S is greater than j omega. So if I use infinity here, then you will take a common factor, j omega minus S. This is a common factor to t. Now, if you plug in infinity for t, then if this number is positive, then it's infinity. If it's negative, then it's 0. I mean, with the exponent, right? Because the exponent, e to the power of minus infinity, is 0. But
Yes.
e to the power of infinity is infinity. So I just told you that S is greater than j omega. It's a greater number than j omega. So, which makes this difference to be negative. That was the only thing I wanted you to observe.
Okay. Thank you.
Okay, no problem. Any other?
Yes, doctor. In this example and other examples that we took before, are we required just to memorize the Laplace transformation, or should we always use this method to solve the function and find the Laplace transformation?
I expect you to be able to derive the Laplace transform from the integral definition. For some examples later, maybe we will have Laplace table for some most common. I expect you to be able to derive it in your own.
Okay.
So you're expected to be able to derive it, and you're expected to be able to use the Laplace transform tables, and you're also expected to be able to use the Laplace transform properties that we will discuss later. And then I expected to be able to do the inverse Laplace transform. And it will take us about 2 to 3 weeks to cover the entire thing. Okay?
Okay, clear.
All right. Let us take another example, but for the cosine function. Let me do the same trick that we just did. I'll just copy it. And I'll also copy the definition. Maybe let me put it here. Okay. This is the definition on top of the slide, and we have the identities here. Now, you saw the sine function. This will be similar. Please do it in your own. So is 5 minutes okay? Or do you think you need less time? Okay, do it for 5 minutes. You guys got it? Any answers?
Yes, I got it.
Good. Exactly the same?
Yes.
Good. Mazen, you got a different answer, so what did you get?
Yes, I got the same denominator, but the numerator was j omega.
Okay. So maybe there was some computational error. Did you use Euler's formula for the cosine function?
Yes.
Okay. Any other attempts? All right. So let us look at the solution. Let me just remove these guys. Then same idea. You basically replace the cosine with its Euler formula's alternative. Then we have e to the power j omega, a to the power minus st. So this will become e to the power of j omega minus s. The entire thing multiplied by t. Why do we do that? To take a common factor, because the derivative with respect to t. So we care about having this easier to integrate. Oh, so
That's not visible.
I don't know what happened. All right. Can you see it now?
No.
No. Still.
All right. How about now?
Now, okay, we can see.
Good. All right. So we take a common factor so that because we're integrating with respect to t, so this j omega minus s is just some constant with respect to t, because this we're integrating with respect to t, so everything else becomes a constant, right? And once you do that integral, you get 1 over s plus j omega, and then you get that thing plus 1 over s minus j omega for the other term, for the other integral, and everything is divided by 2. So since somebody got some difficulties, let us go from this step to here, right? So if we take a common denominator, in the denominator, what will we have? We will have s squared minus j omega s plus j omega s plus omega squared. Because j minus j omega, the j's will give you minus 1 and you have a negative sign, so that you will have a plus omega squared. So the numerator will be the following. For the first term, the numerator will be s minus j omega. For the second term, the numerator will be s plus j omega. These two cancel out. So you will have 2s over s squared plus omega squared. But this 2 is cancelled with this 2. And eventually you get the result. Clear? Any questions? Yes, Faisal.
Doctor, once we integrate the second part of the equation, which is e to the power of minus j wt multiplied by minus e to the power of minus st, we should get 1 over j w plus s and a negative sign, right?
Correct.
But we have here a plus sign for the fraction.
Maybe it's going for the first term.
Can you show me how can we break down the integral part?
Okay, let me see. Let me remove this. Did you derive it on your own?
Yes.
And you get the correct result?
No.
Okay. All right. So with Euler's formula, the cosine is 1 over j omega plus e to the power minus j omega. Okay, good. So at least we know that. All right. So let us do that. Let us go from here. So to this integral, this is correct, this is correct. So basically the integral here is 0 to infinity e to the power j omega minus s t. I'll drop the dt. And here we have 0 to infinity to the power of minus j omega plus s t, right? This first term will be 1 over j omega minus s e to the power, the same thing, j omega minus s multiplied by t, right? This is 0 to infinity. I'm just looking at the first one, okay?
Yes, yes.
Okay, let me just erase this too. Okay. When I substitute infinity, this will vanish. So we have the minus sign because I'm substituting 0, 1 over j omega minus s. So this will give me, if I cancel this sign, it will give me s minus j omega. So actually this guy corresponds to the second term here. I think that's the source of confusion. For the other guy, it will go to the first term. And we can easily see that because if I integrate the second guy over here, I'll have 1 over minus j omega minus s e to the power of minus j omega plus s with a common factor t. Because I'm substituting 0 and infinity, when I go to the 0 part, I'll have a minus sign which will cancel this minus sign, and we'll have 1 over j omega plus s.
Yes, yes, it's clear. I think I forget the minus sign of the integral.
Yeah,
Yeah.
yeah, so there are some steps skipped here, but it is correct.
Thank you, Doctor.
No problem. All right. I'll give you one more exercise to solve this and use integration by parts. So we have the following function. You have a ramp up to time 2, and then you get 0. And this ramp is scaled. So this is the function, 0.5t e to the power of minus st. Use integration by parts, solve it. Can you guys do that?
We will try.
All right. Do you want to try it? Or should we go to the next one? All right. Try that. Let's go. So how much time do you need? 3 minutes? 5 minutes? Give me a suggestion. All right. Let's do 4. All right, let me grab the rule for the integration by parts for you. I'll put it in the slide so you can just use it. Okay. We'll put it over here. You don't see it, right? The slide. Yeah, I think whenever I edit it, it goes away. I don't know why, but I'm actually sharing it right now. So the integration by part is here and on top of the slide. Okay, any success? Right, what is the answer, Faisal? So Mazen is saying minus s plus 1 over s square e square. Faisal, what is your answer?
I got 1 over s multiplied by e to the power of minus 2s minus e to the power of minus 2s minus 1 over 2s squared.
Okay. So honestly, I'm not going to solve this in the board, but the reason I asked you to do it by hand is that later, when we use the Laplace transform properties, we will have some tricks and techniques that make it easier to find the Laplace transform sometimes. Because if you look at this function, we can think about it as a summation of multiple functions. This guy is equal to a ramp here from 0 to infinity minus, let's say, another ramp that is shifted, right? And then minus a step at 1. I mean, it might seem complicated to add 3 terms, but we will see that using the Laplace transform properties and table, we can easily get the Laplace transform of this guy. We can easily get the Laplace transform of this guy. We can easily get the Laplace transform of this guy. So if I just take this minus that, we get this function, and its Laplace transform immediately. But if we use the integration by part, sometimes it might take a little bit of a lengthier route. So we solved enough examples so far, so I'm not going to do this by parts during the lecture. But it's a good exercise for you. So do you have any conceptual questions? I mean, once you do the integration by parts and try to find it, like, is there something that you have a question about? Other than, let's say, you ask me to solve it. My question here is conceptual, like if there is something that's not clear in terms of the methodology. Do you have any question about it? Okay. There are no questions. We can keep going. So we have, okay. We said something about the step, right? The step, the Laplace transform of it is 1 over s. And if I have a step function like this one, let's say L is infinity. Suppose L is infinity, then it will be a over s. Now we have a rectangular pulse in which at L we go to 0. So it will be different. And then we will have, I mean, again, using the Laplace transform properties, we can just say this is a step minus a shifted step at L. And then we will have the Laplace transform of this guy minus the Laplace transform of this guy. Let me just show it to you. Let me explain this. Okay. So now we have this function, okay? We can solve it. We can find its Laplace transform in 2 ways. The first way is just to use the integral directly. The second way is try to analyze it and maybe use, let's say, summation or subtraction of functions. For example, this function is equal to a step, right, with a as magnitude, minus another step that is shifted. Do you agree with that? Do you guys agree with this?
Yes.
Okay. So we have these two. So you see here what I'm trying to do, instead of finding the Laplace transform of the function using the integral, if I can split it into 2 easier functions and I can find the Laplace transform of each of them immediately. For the step input, the Laplace transform was 1 over s. Now this is just multiplied by a, so it's just 1 over a over s. This is the first term. The second term, it's a shifted step. We saw something similar earlier. If you have a shift in time, let's say with L, then it's the same guy, A over S, you just multiply it by an exponent minus SL, which constitutes to this shift. We did that earlier. Let me go back and remind you of last time. We had the following function. The power of minus 2s because it's a shift. So if I just shift it, then I can just multiply it by an exponent, which is a property that we will explore later. So if I combine the two, this will give me A over S multiplied by 1 minus e to the power minus SL, which is identical to this result. Or I can still use the integral. And if I use the integral, we have f of t to the power minus st, which is equal to 0 to L plus L to infinity. From L to infinity, it is 0, so this is gone. And then I can find this integral and get a over s1 minus s e to the power of minus sl. So there is a skipped step, so let's maybe try to solve this integral. So this part is 0, right? So we're done with this part. We're only left with this part. Now let us solve it. Is the screen still frozen?
I see just the example of a shifted step and nothing is changing.
Okay. Let me share the screen again. How about now?
We see nothing. Yes, now it's clear.
Okay, it's clear now.
Okay, good. All right. So for this guy, I can take a as a common factor, right? And then we have 1 over minus s e to the power of minus st, right? And this is from 0 to L, which is equal to a. If I substitute L here, then I have e to the power of minus SL over minus s, then minus, I substitute 0, I get 1, I have minus s, right? Just take a over s as a common factor and you will have this guy. So there are multiple ways to get the transform. Always you can do it by the definition, but sometimes there are ways and techniques to get it like alternatively. If you have some information of, let's say, a Laplace table or some knowledge about the properties, then you can implement and find the Laplace transform. Maybe for this example, it was not much easier, but for, let's say, this example, it will be much easier. So it really depends on the example at hand. So you need to be comfortable with using the integral definition and also the properties on the table later. So as we proceed, you will see those. So with that, let's talk about some properties of Laplace transform. For example, we say, so the Laplace transform has the property of linearity, meaning it's a linear operator. So if I have an A and F, so the Laplace transform of AF plus BG is equal to A multiplied by the Laplace transform of F alone plus B, the Laplace transform of G. Why is this true? Simply, we can prove it. So apply the integral and observe it from the properties of integrals. So this is the function we want to find its Laplace transform, AF plus BG. We have an integral. I can split the integral into two parts because of the summation here, right? And we have A multiplied by this integral and B multiplied by this integral. Then I can take the A and the B outside, and then we can observe that this guy is simply the Laplace transform of F, and this guy is the Laplace transform of G, and hence we have the linear operator. The other property is multiplication by an exponential. So this is an important property. So if I have a function f of t and I multiply it by an exponential, then the Laplace transform is just basically the Laplace transform of f with a shifted variable. To see that, look at the following. We have Laplace transform of f multiplied by the exponent, which is equal to the Laplace transform of f e to the power of minus at e to the power of minus st. This guy is simply minus a plus s t dt, which is the Laplace transform of s plus a. Why? Because the original definition was f of s is equal to small f of t, the integral of small f of t, e to the power of minus st dt. This was f of s, right? Notice, if s is the variable, then everything else is pretty much fixed, right? And you take the integral with respect to t. Now, instead of s, we have s plus a, right? So if you call this s tilde or s prime or whatever, or s bar, then this is just the Laplace, this is just capital F of s prime or f bar, right? Similarly, where s bar here is just s plus a. So this is an important property. So if I have, let's say, a sine function, sine omega t, then this sine is multiplied by some exponent, let's say minus 5t. If you want to find the Laplace transform of this guy using the definition, then it might get hard it might get harder to find the result. But if I know the Laplace transform of the sine function, which is something we can easily know, and we can write it as a property or in a Laplace transform table, then whenever I multiply the sine function by an exponent, then immediately I can just say, okay, because I know the Laplace transform of the sine, and this is multiplied by exponent, I can just shift the output by 5. So for the sine function, the Laplace transform was omega over s squared. So here we have s plus 5 squared because we shifted it due to the exponent. Then we have plus omega squared. Right? Why? Because the Laplace transform of the sine was omega over s squared plus omega squared. So because I know this, and I have a sine function multiplied by an exponent with a shift of minus 5t, then I can just, instead of having s squared, I can substitute this with s plus 5, and that's it. So we can skip the extra, let's say, computational steps. So I'll stop here for today. Please let me know if you have any questions. So next time we will keep discussing the properties, and then we try to use them and show and demonstrate how they can help us find the Laplace transform of a lot of functions. So again, I need you to be comfortable using the definition, and which is the integral, and also I need you to be comfortable to learn the properties, and also later use the inverse Laplace transform and all of that. Okay? So with that, we conclude the lecture for today. Please let me know if you have any questions. Otherwise, feel free to leave the session.